Standard symbols are used to communicate the components of an electric circuit. A single cell is represented as two parallel lines, the positive terminal being longer than the negative. In this flashlight, there are two cells in series. Our circuit diagram shows both of them. Metal conductors connect the cells to the light bulb. Conductors are represented in circuit diagrams as lines. Finally, the load here is a light bulb. The symbol for a bulb is this. In general, any load or resistor is shown as a jagged line.
I see you have diagrammed your circuit. Conducting wires connected to a resistor, which is
the bulb.
And we figured out how to build the voltage size.
Thanks to Mr. Volta for the idea.
I can't wait. Let's see what you can do.
Ready to make the final connection?
Here goes nothing.
You were right. Nothing.
Well, one thing's for sure. It isn't the brightest bulb on the porch.
What did you expect for 36 cents?
Well, if what we've done is correct, then there just isn't enough electric energy being converted to light the bulb.
I probably should have given you this.
What is it?
It's a light-emitting diode, an LED. Try it in place of your bulb.
Well, it looks like it might need a little less energy.
Okay, it's ready to go.
And?
Ta-da!
Well, there's some light there.
That's great. Although this pile of coins isn't as effective as a dry cell, the principles behind the two are the same.
What is a hybrid electric vehicle?
Well, as the name suggests, a hybrid electric vehicle is one that uses two power sources. In this case, a conventional gasoline-powered engine, as well as electricity stored in batteries.
So why even have one?
Well, if you want to build a pure electric car, you would have to carry really heavy batteries, and it's not really practical. So what we do is that we use a small amount of batteries that will get you your daily driving, and then we use a small gasoline engine to use on long distance driving.
Well, let's see the engine. There we go.
So here we have two electric motors and the motor controllers, and our small 3-cylinder gasoline engine. And with electric power, people can drive to and from work just using electric power, and they don't produce any emissions. So it cuts down a lot on urban air pollution.
So where are the batteries located?
Well, the batteries take up a lot of space, so we have them located in underneath the rear seat. We've taken the seat out so you can get a better look at them. You can see they're quite large, and they weigh about 600 pounds.
And how far do they go on one charge?
You go about 50 to 70 kilometers. It really depends on how you drive, just like your fuel economy in your regular car changes. The main problem with today's electric vehicles is the batteries simply do not store enough energy. So companies are doing research around the world on increasing the energy density so you can store more energy for a given weight or volume of battery. One example is Ford's sodium sulfur battery, where they're aiming for storing 3 times more energy than our nickel cadmium batteries. So that would give a vehicle a range of 200 to 300 kilometers on a single charge.
When will we be able to see more electric vehicles on the road?
Well, you won't see them in Alberta for quite a number of years yet. Our air is relatively clean, and our winters require a lot of energy just to heat the car. Where you'll see them first is likely in California, where they have heavy pollution in their large cities, and that's where the government has put in laws mandating electric vehicles starting in 1998.
Before, we saw that the voltage changes across the cell and the load.
Let's start at the cell.
It's a whopping 4.75 volts.
And what about across the LED?
It's 1.75 volts, the same magnitude.
Well, let's determine the current then.
I'll hook that up.
I bet it's not very much.
You're right. It's 0.30 milliamps.
That is extremely small, but you know, even a very small amount of current can still be dangerous.
How so?
The cells of your body respond to an electric current. Just a few milliamperes of current can be painful.
Pain like when you get a shock from the carpet?
Yes, and about 1/10 of an amp can cause a heart fibrillation.
And that means?
Your heart beats irregularly or very fast. As a result, your blood doesn't flow properly, if at all.
Tell me about the bionic glove.
Well, I'm a physiotherapist, and in physiotherapy we use electrical stimulation in a number of applications, and this is a very specific application, using electrical stimulation to paralyze muscles so that the muscles can be made to move. And it very grossly mimics the signal that the brain would normally send out to the muscles, but it can't get through because of an injury. So on the back of this glove here, we have a device, a microprocessor controller that provides or produces electrical stimulation. It goes through the wires to metal mesh contacts inside of the glove. Now that contact, when the glove is put on, meets up with this metal stud, and the current actually flows through the electrodes through the skin and causes the muscles to contract.
Is it safe to apply electrical current to the skin?
Well, with this particular application, we are looking at a very localized area of application. So we're not applying electrodes across his heart or any of the important organs, which could actually be potentially dangerous. We're not looking at applying it over his throat, which is also could cause potential problems.
So what are the amounts of voltage and current?
Well, the pulses you can hear, the clicking, are pulses of about 30 volts. And that's between this electrode and this electrode. But that's like pressure in a tap that's closed. Opening the tap is equivalent to making contact with the skin, and now those pulses of current are flowing through my skin. So about 30 milliamp pulses, 30 volts, that translates into a resistance of about 1 kilo or 1,000 ohms.
So the people who are using this can bring their wrist back. They don't have any finger movement and they don't have any thumb movement. So we'll turn the stimulation on, and you can see that as he brings his wrist back, the muscles stimulate to close his hand and then to open it. Right now this is a research device and we're doing clinical trials, but our hope is that in the next little while this will move from a research setting into the real world.
You know the potential difference and the current produced by your voltaic pile. What energy is being transferred?
We begin by determining the charge flowing.
Current is charge divided by time, so charge is current times time.
Let's stick to 1 minute as the time interval.
So that is 0.300 milliamps times 60 seconds.
That gives 18 millicoulombs.
And change in energy is charge times the voltage.
So that's 18 millicoulombs times 1.75 volts.
No wonder the light bulb wouldn't light.
Yeah, it's only 32 millijoules.
Only a fraction of the energy that was converted in the bulb earlier.
Right.
Well, I think we developed two very big ideas today.
Energy is conserved. The energy stored in a cell is only converted to other forms of energy.
And
charge is conserved. The cell doesn't make any electrons, and the load doesn't destroy any.
good show. I hope it was clear just how dangerous electric current can be.
Oh yeah, extremely small currents can be painful.
And there's enough current running through a light bulb to kill.
That's right, because if you become part of the circuit, you act like a resistor.
Which means the energy is transferred to me.
That's the danger.